Good morning, students. We are in the 10th lecture of the first unit of water resource engineering. We are in the point water requirements of soil. Okay. So in the last two lectures, we have seen the different terms associated with water requirement of crops, such as crop period, base period, irrigation frequency, uh, delta of a crop, and duty of water. These all terms we have seen, and we have also seen the relationship between duty and delta. Now in this lecture we'll study the different types of soils, different types of soil water, as well as soil moisture and irrigationship relation, and lastly we'll see the consumptive use in irrigation. Okay, so we'll start with types of soil. Okay, the ability of soil to hold moisture and the amount of moisture it can hold will greatly affect the irrigation schedule. Okay, so the ability of a soil in order to hold water, which is irrigation water, which is available to it, and the amount of water it can hold in itself inside its pore, it will greatly affect the irrigation schedule. Okay, for example, if a soil can absorb or can hold more amount of moisture or more amount of water, uh, then the water available for the crops will be more. And if the soil is not able to hold more moisture, then the water available to the crop will be very less. Now soil is made up of these particles: sand, silt, and clay. Okay, the percentage of each of these three particles is what determines the actual soil structure. Okay, so in every soil which is used for agriculture, it is made up of the soil is made up of three components, that is sand, silt, and clay. Okay, now the percentage of the respective particles can vary. In some soils the percentage of clay will be more, in some soils the percentage of silt will be more, and in some soils the percentage of sand will be more. And depending upon those different percentages, we get uh, a number of different soil mixtures. Okay, uh, now the percentage of each of these three particles, depending upon the percentage of each of these three particles, the property of the soil will change. Okay, there are some important points in this diagram uh, which are related to our subject. Now one is the water holding capacity of the soil. Okay, now as we seen in the first point, if the soil is able to hold water or hold moisture at a greater capacity, then the water available for the crops is more. So it is a good property, water holding capacity. Now if in a soil sample the percentage of clay is high, okay, if the percentage of clay is high, that means the water holding capacity will be high. Okay, and if the percentage of sand in a soil particle is more, then the water holding capacity of that soil will be low. Why? Because individually if we see, the water holding capacity of the clay is very high as compared to sand. So if a soil contains more amount of clay, it will be greatly able to absorb water or hold water as compared to a soil particle which contains more sand particles. Okay, next is ability to store plant nutrients. Okay, so in this case this is also a good property. Okay, if the soil is able to store more plant nutrients, it is we call it as a good soil for agriculture. Now if it is a clay particle, the ability to store plant nutrients is high in clay. In sand it is very poor. Okay. So if our soil particles contain more clay, then that soil has greater ability to store plant nutrients. But if our soil has more amount of sand particles, then it has very less ability to store plant nutrients. Okay. Next is the nutrient supplying capacity. In this case also, for clay particles it is high, and for sand particles it is low. Okay. Next important point is internal drainage. Okay. Now internal drainage for clay is very slow, and for sand it is high, or we can say it is very fast. Okay. So this can be either good or bad. Good in the sense that those clay particles will be able to hold water or hold moisture for a very long time, and sand won't be able to do that. But if we see look at the bad side, mm, uh, if there is no drainage of internal drainage in clay, okay, there can be a problem of waterlogging. Okay, which is not the case in sand particle. Okay. So these are some important properties of soil depending upon the different sand, silt and soil sands, silt and clay composition. You can pause the video and you can see the different properties. Okay. We'll go to the next slide. It is types of soil water. Okay. Now soil water is the term for water found in naturally occurring soil. Okay. It is the water which is found inside of the soil pores. Now there are three main types of soil water. They are gravitational water, capillary water and hygroscopic water. We'll see all these three types. First we'll see what is meant by gravitational water. Okay. It is the free water moving through soil by the force of gravity. Okay, when the water percolates into the soil, it moves downward, okay, due to the action of gravity. It is largely found in the macropores of soil, and very little gravitational water is available to plants. Why? Because it drains rapidly down the water table in all except the most compact of soil. Okay. So gravitational water, it is free flowing water. Okay. It moves through the soil in the downward direction, and it moves very fast. Okay. And it exits the soil zone also very fast. Okay. So because of this, very little gravitational water is available to plants, okay, for its use. Next is the capillary water. It is the water held in the micropores of the soil, and is the water that composes the soil solution. Capillary water is held in the soil because the surface tension properties, that is cohesion and adhesion of the soil, are stronger than the forces of gravity. Okay. Capillary water is the main water that is available to plants, as it is trapped in the soil solution right next to the roots of the plant. Okay. So capillary water is the main water which is available to the uh, crops or the roots of the crop. This is because the surface tension properties of the soil micropores, that is cohesion and adhesion properties, are very strong as compared to the force of gravity. Okay. So what happens, the water, this capillary water remains suspended in water, remains suspended in soil right next to the root zone of the plants. Okay. The zone where the roots of the plants or the crops reach. So this water, capillary water, is directly available to the plants, and they can take it, they can take the water from the capillary water. Last is the hygroscopic water. It forms as a very thin film surrounding soil particles, and is generally not available to the plant. Okay, this type of soil water is bound so tightly to the soil by adhesion properties that very little of it can be taken up by plant roots. Okay, so this hygroscopic water, it forms as a very thin film surrounding the soil particles. It surrounds the soil particles in the form of a very thin film or a layer. Now this type of water is tightly bounded to the soil because of the adhesion properties. Okay, the adhesion between the soil and the hygroscopic water is very high. So this water, very little of that water can be taken up by the plant roots. Okay, so next we have finished types of soils and types of soil waters. Next we'll see soil moisture and irrigation relationship. Okay, now before we see the points, we'll first discuss the diagram. Okay, this is the ground surface, this is the ground level. Okay, above which some amount of crop is visible and the remaining part of the crop is below the ground level. Okay, now this layer, okay, or this zone in which the root of the plant is visible, this is known as the soil zone or the root zone. Okay, the zone below the root zone or soil zone is the intermediate zone, and below the intermediate zone is the capillary zone where the water will remain suspended. Okay, below the capillary zone you will see this dotted line. This is nothing but the water table. Now below the water table there is free flowing groundwater, and below the groundwater is the impervious strata. Okay, now the water below the water table is known as groundwater, and above the water table is known as soil mixture. Okay, so the water in this zone, it is known as soil mixture, soil moisture, sorry. Now below the ground surface is the soil zone or the root zone that is penetrated by the roots of vegetation, just as I have told you. Now this zone is most important from the irrigation point of view because the plant takes their water supply from this zone. Okay, the water which the plant is going to take for its growth, the crop is going to take for its growth, it is all taken from this zone, that is the soil zone or the root zone. Okay, now when water falls over the ground, a part of it gets absorbed in the root zone. Okay, the some part of the water which falls on the ground gets absorbed in the root zone. Okay, and this water which is absorbed in the root zone is available for the growth of crops, but the rest of the water flows downward under the action of gravity, and it falls downward and meets the groundwater. Okay, which is not available for the plants. Okay, so this was the soil moisture irrigation relationship. We'll see the next point, that is the consumptive use. Okay, now consumptive use for a particular crop may be defined as the total amount of water used by the plant in transpiration and evaporation from adjacent soil or from plant leaves in any specified time. So what is consumptive use for a particular crop? It is the in simple words, it is the total amount of water required by the crops, okay, for its growth, as well as the water which gets lost in evaporation. Okay, this total amount of water is known as the consumptive use. Okay, it is used, this water is used by the plant in transpiration. Transpiration is the building of the plant tissues, okay, plant leaves, etc., and evaporation from adjacent soil or from plant leaves. Okay, evaporation from the plant leaves is known as evapotranspiration. Okay, so the total amount of water required for transpiration, that is building of plant tissues, leaves, and as well as evaporation from adjacent soil or leaves, is known as the consumptive use for a particular crop. Okay, now the values of consumptive use may be different for different crops and may be different for the same crop at different times and places. Okay, we'll see this. It means the consumptive use may be different for different crops. It means, for example, if we take two different crops, one is sugarcane, one is wheat. uh, for example, sugarcane requires more water for transpiration, that is building of the plant tissues. Okay, so the consumptive use of sugarcane is more, but wheat requires very less amount of water for building its plant tissues, so the consumptive use of it is very less. Also, the consumptive use may be different for the same crop at different times and places. Okay, for example, if we grow wheat in a wet climate, okay, such as Konkan or Western Maharashtra, and the similar wheat crop you grow in a dry climate such as Rajasthan, okay, there also the consumptive use may differ. Why? Because if you consider Rajasthan, it is a very hot and dry region, so there will be losses in the form of evaporation from adjacent soils or from plant leaves. Okay, so more amount of water will be lost, so the consumptive use for a wheat crop in Rajasthan may be more. Okay, I hope you understood this. In fact, the consumptive use for a given crop at a given place may vary throughout the day, throughout the month, and throughout the crop period. Now, this is very important. The consumptive use for for the same crop at the same place, it can vary throughout a single day, it can vary throughout the month, and it can vary throughout the crop period or the base period. Because if we see in the afternoon, it is very hot, so more water will be evaporated, okay, from the soils and from the plant leaves. If it is night time, less water will be evaporated, so the consumptive use will change depending upon the time of the day, the time of the month, or throughout the crop period. Okay, now the values of daily consumptive use or monthly consumptive use are generally determined for a given crop and at a given place. Okay, values of daily consumptive use are generally determined for a given crop and at a given place. Okay, now next point we'll see the effective rainfall. The precipitation falling during the growing period of a crop that is available to meet the evapotranspiration needs of the crop is called effective rainfall. Okay, now if we go to the last slide. Okay, if you go to the last slide, what was consumptive use? It was total amount of water used by the plant in transpiration and evaporation. That means it is another word for evapotranspiration. Okay, uh, so what is effective rainfall? It is the precipitation falling during the growing period of a crop that is available to meet the evapotranspiration needs of the crop is called effective rainfall. Okay, so the rainfall which falls during the crop period or during the growing period of crop, and uh, it meets the evapotranspiration, that means that rainwater is utilized for transpiration, that is building of plant tissues, as well as for evaporation from soil and plant leaves, then that rainfall is known as the effective rainfall. Now this effective rainfall, it does not include precipitation lost through deep percolation below the root zone or the water lost as surface runoff. Okay, that you have to keep in mind. So we have seen what is consumptive use, okay, and what is effective rainfall. Now consumptive is the total water required by the plant to meet its transpiration evapotranspiration needs, and some amount of that consumptive use requirement is provided by effective rainfall, and the other requirement we have to fulfill it with the help of irrigation. Okay, now we'll see the consumptive irrigation requirement. The consumptive irrigation requirement is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop during its full growth. Okay, it is therefore nothing but the consumptive use itself, but exclusive of effective precipitation, stored soil moisture, or groundwater. Okay, now uh, we will consider that stored soil moisture and groundwater is negligible. We'll ignore both this point. Therefore we can write that consumptive irrigation requirement is nothing but the consumptive use itself, but exclusive of effective rainfall. That means consumptive irrigation requirement is consumptive use minus effective rainfall. If you have not understood, we'll again see. Okay, now what is consumptive use? You have seen it is the total water used by the plant for its evapotranspiration needs. Okay, now some amount of that water is provided by effective rainfall. Okay, so some amount of the consumptive use requirement will be provided by rainfall water, but the remaining amount of water required for consumptive use should be made with the help of irrigation water. So uh, what is irrigation water requirement? It is nothing but consumptive irrigation requirement, CIR, which is consumptive use minus effective rainfall. I hope you understood this. Okay, what is CIR? It is the amount of irrigation water required in order to meet the evapotranspiration needs. Okay, so it is nothing but consumptive use minus effective rainfall. Okay, now we'll see a problem on consumptive irrigation requirement. Okay, the following table gives the value of consumptive use and effective rainfall for the period shown against them for a jawar crop sown at Bellary in Karnataka state. The period of growth is from 16th October to 2nd February, that is 110 days. Okay, period of growth, it is nothing but the crop period. It is 110 days from 16th October to 2nd February. Determine the consumptive irrigation requirement for of these crops. Uh, so the consumptive use is shown month wise. Okay, first it is shown for the month of October. So the consumptive use is 37 millimeter. For November 1 to 30 it is 84.2 millimeter. Then for December 1st December to 31st December, then 1st January to 31st January, and lastly for the month of February from 1st to 2nd February. Okay, the consumptive use is 13.3. So we have to find out the consumptive irrigation requirement. That means how much amount of irrigation water we will have to provide to meet the remaining consumptive use need. Okay, so the total consumptive use of a plant, for example in October month for 15 days, it was 37 millimeter. Now 30.8 millimeter out of those was provided by the effective rainfall. Okay, so common sense tells us that the irrigation water which we will have to provide will be consumptive use minus effective irrigation. So we will solve the problem in the, so this is the solution. The table in the question will extend it. Okay, now CIR, that is consumptive irrigation requirement, it is difference between CU minus RE. So column 4, that is CIR, is obtained by subtracting column 3, which is effective rainfall, from the column 2, that is consumptive use. Okay, so total consumptive use of plant is 37 millimeter. Out of 37 millimeter, the requirement made by irrigation effective rainfall is 30.8. So how much irrigation water will be required is 6.2 millimeter for the month of October. Similarly, we will calculate for the month of November, December, January and February. So this is the consumptive irrigation requirement for each month. Okay, so the total consumptive irrigation requirement for 110 days, that is from October 16 to February 2. Okay, it is the addition of all the rows in column 4. Okay, and it comes out to be 416.2 millimeter or 41.62 centimeter. Okay, hence the total consumptive irrigation requirement of the jawar crop in Bellary of Karnataka is 41.62 centimeter. Okay, so in this lecture we have seen types of soil water, soil moisture and irrigation relationship, and lastly we have seen the consumptive use of a crop. Okay, so thank you.